Welcome to a code report solution video. In this video, we're going to be covering the solution to problem 3A of Advent of Code in APL. So let's hop over to the problem statement to take a look. So here is the problem statement on the adventofcode.com website. I'm not going to read through the full problem statement. I encourage you to check it out if my summarization doesn't make sense. But basically, we're given a single input, a 2D grid of periods and octothorpes, aka the hash or pound symbols. And the periods represent an open square, and the octothorpes represent a tree. So that's pretty straightforward. Periods is empty space, octothorpe equals a tree. And basically what the question asks you to do is imagine that this 2D grid is projected out horizontally, and that you start in the top left-hand corner, and then each turn you go down 1 and right 3. So we start here, then we go down 1, right 3, down 1, right 3, and then we've hit an octothorpe. So this represents a tree, and the question is basically asking us, how many trees are we going to hit before we get to the bottom row? And for this question, I believe the answer is 7 trees. So hopefully that makes sense. You can see here's the visualization of each of the trees that we've hit. Let's hop over to Dialog APL now and take a look at how to solve this. So here we are in Dialog APL. I have preloaded our input, which is our 2D map. And the first thing we want to do is figure out how to horizontally project this. So the easiest way to do this is just by using the comma symbol, which is for catenation. And if we do this, we'll end up with our 3 grids side by side. And we're not going to use this in our final solution, so I'm just hard coding the fact that we need to do this 3 times in order to project it long enough to get down to the last row. But for now, we're going to stick with it. But one of the irritating things here is that we have to type out input 3 times, which is very irritating. So we can reduce this down to 2 by using the power operator. So if we type input, parentheses, comma for catenation, the power operator, which is the star with 2 dots over it, and then 2, which is going to repeat this comma operation twice, which is the number of times we see it in the code above, and then type input as our right argument again, this is going to catenate our input grid 3 times. This is still irritating though because we have stated input twice here, and so we can get this down to 1 by removing the left argument and using the commute operator, which is going to say if I have omitted my left argument, use my right argument as my left argument. So doing this, we can get our 3 grids side by side, and it's quite magical. So note that this is twice, even though we're seeing our grid 3 times, but we have the number 2 here because we only need to use catenation twice. And this is the power operator, this is the commute operator. Pretty fancy. So now that we have our projected horizontally grid, or our horizontally projected grid, we need to get the coordinates to index into this 2-dimensional grid to pull out the locations that we're going to visit. So the way that we can do this is first by getting the number of rows. So we'll call this R for rows. And we can do this a couple of different ways. And the way that we're going to do it is by pulling out the first element of our shape of our input. So the shape of our input, so actually let's just build up a matrix that has different dimensions. So this is a 2-dimensional matrix with 3 rows and 4 columns. And if we want to get out the number of rows, we basically can just ask for shape, and then that'll give us 3, 4. And then we want the first number from this shape, which is we can use get using the first symbol. So we've set R to be equal to the number of rows. And now that we have this, we can generate a list of numbers from 0 to 10 using iota of R. And so now to get our list of coordinates, we just need to multiply the coordinate pair of 1, 3 composed with multiplication. And we need to apply this. So this is now a unary function that multiplies something by 1 and 3. And then we just need to do this over our list of numbers from 0 to 10. And if we do this, we get the following list. And this works because we have rank polymorphism in APL, which means that multiplication doesn't just work for integers. It works for integers with arrays, arrays with arrays, etc. It's awesome. And so now we have our list of coordinates. And now that we have this, we can just combine this with the catenate power to commute of input and use the bracket operators to index into our two-dimensional grid. And if we do this, we end up with each of the cells of our two-dimensional grid that we have visited. And so the octothorpes represent the number of trees, so we just need to now do a monadic octothorpe equals, and that's going to turn all of the trees or octothorpes into ones and everything else to zeros. And then once we have this, we just do a plus reduce to get the count. So this is a solution. It's not a very good solution because it's pretty noisy and cryptic, but it's a solution that we can start from. So I mentioned at the beginning that this is not going to end up in our final solution. And that's because you can make the observation that we don't actually need to project our grid out horizontally. We can just modify our coordinates such that they wrap around to the beginning of the line anytime they exceed the number of columns in our 2D grid. So if you note here, this is our list of coordinates. After, what is this, the fifth element, we start indexing into columns that are greater than our initial grid. So what we can do is if we just get the number of columns in our grid that we started with, so we can do this by doing similar to what we did for the number of rows, but instead we're going to reverse our shape, which gets us the last element, and then we get shape of input. So this is the number of columns. For this example, they're actually the same. And so what we can do now is if we just go the number of columns modulus these values, you can see now anytime we had a 12, a 15, an 18, these have now wrapped around to the beginning of our array, which means that we can avoid the use of all of the power and commute operators and catenation, and we can just directly index into input and get the exact same list. So then when we do this and combine it with a plus reduce octothorpe equals, we get our same answer. So this is basically our solution. We have hard-coded in here C and R, so if we want, we can set up an actual function. So let's go ahead and do that. In dialog 18, there's an experimental feature called multi-line editing. So if you just open up a brace for the start of a defun, which is just what they call a function in APL, you can add the following. So we can go number of rows is equal to the first of the shape of omega. So omega is going to be our argument on the right. So that was what was input before. Then we go columns is equal to the first of the reverse of the shape of omega. And then we can type in what we had before. So plus reduce octothorpe equals omega for our input, bracket, columns modulus. And we can actually pass in our coordinate 1, 3 as an argument, and then compose multiplies for each iota of the number of rows, which is R. And if we do this, the last expression in our defun is going to be what's returned, and so we can test this by saying tree count is equal to, or 1, 3 passed a tree count and input, so this should give us 7. So this is super neat. And if at any point, say I made a mistake and I needed to go back and edit my defun, I could just go paren ed tree count, and then this would open up a pane in the right. So for instance, you know, if I need to debug this, a classic thing is you do you assign to quad, which is output. And so if we do this, you hit escape to close this now. And if we were to do the same thing, it outputs the intermediate, whatever you were writing to quad, which is pretty cool. So that's the end of this video. I know it went pretty quickly, but hopefully you were able to pick something up and learn something. I absolutely love APL due to the fact that algorithms are single character symbols. It enables you to really express different ideas and solve problems different ways very simply. And yeah, I totally encourage you to go download Dialog APL. It's completely free. The link will be in the description of the video if you are interested in checking this out. And as I said before, hope you learned something, hope you enjoyed, hope you have a great day, and we'll see you in the next video.